Hello and welcome to another creative coding video. We're continuing our series of back to basic videos where we go back to the simplest code that we learned, the simpler ideas, and practice those ideas and build interesting new code to create interesting new designs. So it's fun because we're not stretching ourselves too much in terms of coding. And we're creating some new designs and new patterns, and it's a great way for us to practice and revisit those very core ideas which are so important. Today's going to be a fun one, I think, not too long, quite short, but it's a fun idea that we're going to explore, and that is the idea of forces between objects like particles or planets. So let's start off with drawing a picture just to kind of explain the idea. So if you imagine there's a planet here, or a particle like an atom, and maybe there's another one here. Now they may have they might exert a force around them. So if it was an atom, it might have an electrical field around them, an electrical force. If they were planets, they might have a gravitational force. We're not too bothered in this video about which force, and we're not too bothered about getting the exact, mathematical description of those forces. We're just gonna imagine a generic kind of force and just come up with some simple ways of describing them mathematically. If you are interested in exact physics, then please do kind of experiment with doing that yourselves, but we're keeping it simple today. So these two objects, particles, will have force field around them. They'll exert a force, which means that if we're close to them, the force is stronger, and if we're further away from them, the force is weaker. Now I've not drawn these circles very accurately, but you get the idea. If I'm a person or another object, somewhere, let's say if I'm here, I will feel the force from this one more than I will feel the force from this one, because I'm closer to this one, whereas I'm further from this one. So the effect of this one will be weak, and the effect of this one will be quite strong. So the closer I am to the source of that force, the force field, the more I'm going to feel it. If I'm over here, then this will be closer and this will be more distant, and I'll feel this one much more strongly. But I will still feel the effect of this one. It's just that its contribution will be a little less, a little diminished, because I'm further away from it. Now, if these forces were attractive, as in pulling me towards them like gravity, then if I'm here, let me pick another colour. If I'm here, I will probably fall towards this one, because that one is closer and stronger. I feel it more strongly than this one here. I will feel the gravity pull from this planet, but not as strongly. So this one will win. Similarly, if I'm here, I'll fall into this planet and not this one. And it's interesting because there'll be a point somewhere between the two. Let me find another colour to kind of demonstrate that idea. If I'm here, then I will have an equal pull towards the two planets. And that's interesting because that means I've found a point where I won't move. I'll be kind of held in suspended animation, as it were, finely balanced, pulling in both directions, but not moving in either, because they're equally matched. And there is a point in space, if you're in the right position between the moon and the earth, you can find the right point where you're not going to move towards either one. You're just perfectly held between the two. Now, wouldn't it be nice to be able to visualize the kind of the effect, the kind of total effect of these forces from say two particles or even more particles? So let's think about how we might do that. So one thing that we can do that I think is interesting is to consider a whole area in the regions around the sources of a force. So if these are planets, this might be a bit of space, or if these are magnets or particles or atoms, this might be the area near them. We can create a map, as it were, showing us how that force is spread, how it affects the region. So if I'm very close, I might let me colour this in a slightly so if I'm very close to a source of the force, I might end up with very strong colour near there, and as I move away I might have a region coloured differently, because around here the force is not as strong as it is closer to the object, and even further away I might have regions like this. So the same colour kind of means it's the same force that's being felt. Now it won't be an exact circle, I don't think, because the contributions, you know, if I have a point that's here, it's gonna feel the force from this particle as well as this one. So I think it might turn out to be some kind of, maybe an ellipse or some squished egg shape. We'll see, I don't know. It also depends on how we describe mathematically the force, and we'll keep things simple. But I think what will be more interesting is if we have 3 particles, or maybe 4. How does this map change? What does it look like? You know, we might have an interesting kind of region where the force is strong, and then the other regions where the force is not so strong but fairly strong. Might create some interesting designs like that, and obviously as they get closer to other shapes, you know, they'll kind of merge and touch, as it were. So it's interesting to see what kind of designs we end up with. So that's just a kind of a non-scientific, plain English overview of what we're trying to do, where we want to have objects, which might be planets, might be particles, which have some force, and we won't worry too much about describing it like real forces, and we'll pick a point and we'll sum up how much force we are feeling from all the sources, and we'll colour it. So let's try that idea. So let's get coding. So I'm logged into Open Processing as usual, and the most important thing is that I've got my Simple.js library enabled. I've just increased the size of the text so we can see. And I guess the first thing for us to do is, oh yeah, the important thing there is we've got Simple set up, ready for us to start coding. Right, so the first thing we want to do is to create a list of those objects. And if you remember, lists are created in a similar way to this. So we have variable, and instead of that variable being, say, 5 or text like this, we tell our code that we're creating a list by using square brackets, and this is an empty one, we haven't got anything in there. If we had put things in there, it might be something like that. So if you need a refresh on lists, do go back to the earlier tutorial videos that introduced it for the first time. So I've created an empty list and I'm going to use a loop, standard loop there. Let me fix my indenting. There you go. So I'm using a standard loop which counts from 0 to 1, so it will go around twice, I is 0, I is 1, and then it will stop. Again, if you need a reminder about loops and for loops, there are other videos that cover it, and there's one that introduces it specifically, so have a look on the channel at the other videos. And what we're going to do here, we're going to push an object onto that list. So we use push to add to the end of the list. And what is it that we're going to be pushing? Well, our objects, our planets, our particles, we could create quite complicated data structures to describe them, but we don't need to. They're essentially described by two numbers, their position horizontally and vertically, their x and y coordinates. We don't really need much more yet, I don't think, to describe them. So we could say, 300, 400, that would be one object that's pushed there, so that might be something like that. But actually we want to randomize where they appear. So I'm going to create a vector, which is something that P5.js gives us, and it's just a nice way of packaging together 2 or 3 numbers, because vectors have an x and a y and maybe even a z. So we're using vectors as a way of describing where these objects are going to be. So the vector, when we create a vector, we have to say what each of those x and y values are, but here we're going to randomize it. So random number between 0 and 800, that's across, and random number between 0 and 600. So let's just go over what we've done there. Random number between 0 and 800 picks a random number between 0 and 800, and this one will pick a number between 0 and 600. So this vector that we've created, which nicely packages together two numbers, will have an x coordinate between 0 and 800 and a y coordinate between 0 and 600, which is the size of our canvas, 800 by 600. And we're going around this loop twice, so we should have 2 vectors added to that list. Now, just so we are, before we kind of dive into kind of doing forces and things, let's just make sure that those objects are created properly, and let's kind of plot them. It's a good habit to visualize things that you've created, even if you don't use them in the final design. It's good to see that they actually really exist and you haven't made an error. So I'm going to say for, I'm going to work through the list, and modern JavaScript has a really nice way of working through lists, which is something, let's say D, of L. So L was our list, and D becomes each item in the list. So for the first object in that list, the first thing in the list will become D, which is the vector we created. So circle, we're going to just plot a circle for each one. And what are the coordinates of the circle? Well, it's d.x and d.y. That's a nice thing that vectors give us, easy access to the x and y. So let's see if that works. Actually, we need to give a size, don't I, to my circle, size 10. In fact, why don't I give it a colour? So I'm going to say fill, let's say 255 0. Let's create that. And in fact, I'll remove the stroke, so no stroke. So just nice circles without an outline. Let's see if that works. Oh, I've made an error somewhere. Where did I make that error? Line 9. So that should have been a curly bracket there. Oh, another one. Line 9. So what am I doing wrong? So that bracket there, that bracket completes there. I'm missing bracket. I need to make them match up. Great. So you can see the first planet or atom is here and the next one is there. And those are randomly created. Let's run it again. Those two there. Let's run it again. Those two there. So you can see we're creating two objects, two planets, two atoms, and they are being positioned randomly on the canvas. And I'm just showing them just to check that they really do exist. Great. So everything we've done so far is using fairly simple code and simple ideas that we have introduced before. So if any of this was a little bit uncomfortable or very new, do go back and look at the earlier videos where we introduced these ideas for the first time. Randomness is introduced, the idea of a vector, the idea of a list, the idea of a loop, they're all introduced earlier on. They're very kind of basic ideas, but you should be familiar with them. So if you're not, this is a great way of kind of practicing. Right, so now that we've created our planets, we need to visit every point on our map, on our kind of region, and decide how much force is felt at that point, and then color it accordingly. So let's create the loops that will work through every point on the grid. So it'll be a nested loop. There'll be a loop within a loop, one going across and one going down. So let's create the one that goes across. So for x is 0, x counter starts at 0, works all the way up to 800, and we're going to increase it by plus equals 1. So that's the first outer loop. Then we're going to have an inner loop. And I'm just going to copy and paste the code a little bit because it's very similar. And here say y goes up to 600, or just under 599 it goes up to there. And we've done this lots of times, this very familiar inner and outer loop that works through all the x's and all the y's on our canvas. Great. And what are we doing when we visit each point? Well, let's just test that we are visiting points. So I could say, let's fill in, let's color in the dot at x, y. Let's go up in steps of 5 so we don't spend too much time visiting everyone. We should see a colored grid. There you can see, so we're visiting every one of these points and I've colored them black, just filled in that pixel. So we know this is working, we are visiting every point. So at each point we were measuring how much force we felt. That means we need to, let's write in English as it were. So what is sum of force at this point? The sum of the force is the force felt from each object in that list. That means we have to iterate over that list. We have to work through that list. So let's do that. Let's say work through, let's say planets or atoms. That means we say for d of list for, let's say, atom. Let's tidy up our code here as well. Let's call that atom. Give it sensible names. Atom. There. So for atom in the list, for each atom, what are we going to do? where we're going to measure how far we are from our current point. So we are currently at x comma y, and we know that the object is at d.x, or sorry, atom.x and atom.y. I'm just thinking aloud as I type here. It can sometimes help kind of clarify what code is required. So this is helpful. We want to measure the distance from where we are and that atom. And there's a function for that called dist. It's a nice convenience function. We could have done the mathematics ourselves, you know, the using Pythagoras' theorem to square the distances, sum them, and then do a square root, but dist will just do that nicely anyway. And we've used these before. So the distance from xy and atom x and atom y, there. So that distance will be, so let's call that, I don't know, r. So var r equals that distance. So every time we go around this loop, every time we visit an atom, we're working out the distance to that atom, and then we move to the next atom and we work out the distance again. So we somehow need to kind of keep it, remember it. Well, what we can do, we can say var, I don't know, sum of forces or something, I don't know. Let's call it force sum, or total force. Yeah, let's call that total force. Let's start that as 0, and then what we do is we add to it the distance that we measured. So what's this going to do? We start off with a value of 0, we visit the first atom, we work out the distance, and then we add it to this kind of counter. Then we visit the second one, calculate the distance, and add it to that running total. Is that what we want? Not really, because if you remember, the closer we are to an atom, the stronger the force. And what we're doing here is we're adding numbers which are bigger the further away we are. So if I'm far from an atom, this distance r will be large, this distance will be large, and we're estimating a total force which is large. That's wrong. We need small distances to correspond to larger force. So we need to do something with that value, that distance. It's almost like the inverse. So the larger the distance, the weaker the force. So we could say 1 over r. That might be a simple way of doing it. It might be problematic if r is 0, because then dividing by 0 doesn't work. We've actually looked at mathematical functions for looking at sort of decays and bell shapes in an earlier video, and I'd recommend going back to that, because there's nice bell-shaped functions in maths which are really useful and actually do correspond to how some real physical forces work. So instead of 1 over r, what we can do is do an exponential, which is minus the distance. Let's visualize that. So imagine we've got a planet or an atom, and we've got somebody who's sitting here, then somebody who's sitting here. The one who's closer will feel the force more strongly. So let's draw that. This is the distance r that we're calculating, and for the other person the r is much larger. Now, what we want to do when we want to estimate the force, we don't want to use R, because as R gets bigger, we don't want the force to get bigger. We want there to be an opposite relationship. We want, as R gets bigger, we want the force to go down. And we can use things like 1 over R to kind of estimate or model that force. But when R is 0, the 1 over R causes an error, it's infinite. So there are other functions that we can use. We can use things that kind of fall like this, that start at say 1, and this is the bell curve. This is e to the minus r squared, and we've used these before. We've done a previous video introducing interesting mathematical functions that are really useful in creative coding, and this kind of nice exponential decay is one of them. So let's use that instead. And here, and I'd recommend using your own choice of graph plotter. I'm using Desmos here because it's quite nice. And here I'm plotting 1 over x squared, and you can see it does go down as r increases, so the force weakens with distance. But as r gets very small, it kind of explodes. Whereas this one here, the bell curve e to the minus x squared, starts off at a sane value 1 and goes towards 0 but never quite gets there. So we can use that, and that's what we started coding. In fact, I didn't do the square, did I? So I need to do the square. So minus math dot pow for power, r2 for squared. So this thing squares r, then minus, and then exponential. So that'll give us a value from 1 down to 0. So that's quite small. So let's scale it up by 100. So we're adding this scaled estimation of the force to our running total. So as we run through each atom, we kind of sum up how much force we're feeling at that point. And what do we do with that? Well, we do want to plot a point. We want to fill a dot in at xy, but we need to choose a colour that's derived from that kind of total force. And we could say, let's just plot the total force and see what happens, just as a starting kind of experiment. Let's say 0, 0, just to get started. Let's see what happens there. We can kind of iterate as we go along, but let's see what happens here. Let's try that. Okay, so I'm not seeing a lot of variation there. Maybe if I don't visit every dot, if I don't leave any gaps, if I visit every dot, maybe I'll start to see some variation, or maybe I won't. This will take a little bit longer to calculate because I'm visiting every single pixel on that canvas. Okay, so I'm pretty much saturated that. There wasn't much variation, so maybe I've calculated it in a very kind of naive way. So let's have a look at that again. So the distances will be the tens and hundreds of pixels. So that could be something like 10 or 100 or 200 or 400, because that's the distances across the canvas. And then I'm doing an exponential, decaying exponential on that. So actually all the values will be tiny. So if I divide that by 100, that might give me something more interesting to see. Okay, that's interesting. Yep, now we're getting there. If you weren't sure why we made that change, the values of r were in the hundreds, so the distance from here to here might be 400, the distance from here to here might be 300. And And when we do an e to the minus r squared, that value is always going to be tiny. So our running total will be tiny, which is why we were seeing lots of black. By dividing the distance by 100, we are moving into this kind of sweet spot of that bell curve, closer to the lump, which means we can start seeing some interesting variation. So this is nice. This is getting closer to what we wanted. Around here, you can see the more intense field, the force, and as we move away it gets weaker, and then the same here. If we did run it again, we'd just find two different points. Actually, let's do that. Let's run it again. It might take a while, but let's run it again. Okay, they're quite near the edge, aren't they? But again, you can see that the force is around them. It'll be interesting later to see what happens when we add more than one dot, more than one object. In fact, let's do that now. So rather than adding just 2 planets or 2 atoms, let's make 4 and run that. Okay, so you can see these 3 are closer together and their forces merge a little bit, which is why we have this kind of triangle area of red, where around here, anywhere near here, their forces are combined. So it creates an interesting map, and this one on its own is more or less circular because it's far away. It's not able to combine its force with the others. So let's jump this up to say 10. Let's make, I think if I say 10, that actually creates 9, but it doesn't matter. Okay, so this is interesting. We've got a little warning saying that the code, that Open Processing, thinks our code might have an error because it's taking a long time to calculate. It's trying to protect us from our own code, as it were. So we can put this NoProtect at the start of our code to tell it that actually no, our code does take a long time to run. So I'll do that in a minute. But there's many more objects now on our map, and yeah, it did stop it here, didn't it? But you can see they're nicely combined here, and these are a little bit more further apart, so the forces don't combine so much. Let's add that thing at the top that tells it NoProtect there. It gives it a hint to say, look, our code really will take a long time to run. So let's run that again. Oh, okay, so they've all decided to be on the left and bottom. But it's a nice kind of pattern that emerges. Now, I think we can improve how we visualize these kind of the effective force at each point, almost by developing some kind of contour lines. That would be much more striking, I think, than just this kind of fuzzy blobs. I mean, that's what it is. And if you're familiar with physics, you might recognize these as, I don't know, the probabilities of an electron being around a molecule, for example. Don't worry if that doesn't make any sense to you. So before we proceed, I just want to pause and just take stock of what we've done. We've created some random objects, atoms or planets or whatever they are, and we've modeled some kind of force around them, and we've visualized the effective force at any point on this map by combining the forces that you would feel from all of those objects. We haven't worried about what force, whether it's magnetism or electrical force or gravitational force. We've just invented a nice simple mathematical way of describing it. You can experiment yourselves with other ways of modeling that force. So we've created some nice compelling visualizations here with very simple ideas and very simple code. So let's think about how we might move from this kind of force clouds, as it were, these fuzzy maps, to something that shows the contours a little bit more. Now if you think back to, again, that earlier introduction we did to useful mathematical functions, where we came across this bell curve decay, we also came across the sine function, the sine wave which goes up and down. If we apply that, we should get an up and down movement in the effective kind of colour. So as we move away, we should get up, down, up, down, up, down. So sine of x goes like that. So as our values increase, the sine of x goes up and down, like that. So as our effective force goes up, what we plot will go up and down, and that should hopefully create a nice contour design. Let's try it. Let's go back to our code. So the colour we're choosing is not just the total force, but the sign of it. Math.sign total force. Now, do we need to think about scaling it or not? Yes, we do, because the sine value will always go from -1 to +1. So let's not worry about the negative numbers for now. Let's just multiply it by 200, so it goes from -200 to 200. I know that RGB values should go from 0 to 255, but we can ignore the negatives for now. Let's just see the effect it has. It might be good enough for us. Let's try that. Wow, that's really cool. That's the power of algorithmic art. It's really simple ideas. You didn't expect that, did you? Really simple ideas. A little bit of sprinkling of a little bit of maths, and we have some really interesting designs emerging. So these contours are following those fuzzy clouds and converting them into high and low values. So if you look at this lonesome atom here, it has a force field around it, and as we move away the force diminished. And in the previous view there was just the strength of the cloud getting weaker, the cloud was getting thinner. But because we've turned it into a sine function, we can see the up and downs effectively as rings, because the further away we go, as we move away, up and down, up and down, up and down. Actually there's negative values that we kind of ignored. It's probably clipping them to 0, but that's okay. And you can see now the points more clearly, where if you were here, for example, you might feel an equal pull in each direction. So this group of planets or atoms and this one here, the force is balanced perfectly just there. That's fascinating, isn't it? And the same, this cross point here, it means that if I'm there, I'm feeling an equal pull this way as well as in this direction from all these atoms. In fact, all of them actually, because we are considering all the atoms and their force. So this is really interesting, really striking. I think we could stop there. I think that's fascinating. Let's run it one more time to see just the kinds of images we get. It will take a while to run. That's, again, really interesting, isn't it? It's a different configuration of atoms, and the forces, the contours, have kind of had to go around them and move with them. That's really interesting, isn't it? I think, you know, we could remove those yellow dots, but I think they kind of add to the design. It's just really, really nice design. It's very kind of lava, fluid, magnetic kind of forces, something very alien-like about them. Really effective, and you know, the ideas behind it were really simple. I think the fundamental idea of using contours was the key one here. Really, really interesting and powerful. So I'll stop there. I hope you've enjoyed that. So just to summarize, what we wanted to do was go back to basics, use some of the simple code using circles, loops, lists, come up with a simple idea of estimating forces and just visualizing it. And our key magic step was to use the sine function to create these contours. So have a go yourself, experiment yourselves. Maybe you can invent a third type of particle, or you can have fun with a different way of calculating distance or estimating the force, and see what you come up with. Cheers, bye.